Okay, get started. So we just quickly wind up the last week's interference chapter. We were at the very end. I rushed through the last couple of things. I just wanted to quickly review it. And then we'll consider today a new topic, which is diffraction. And we'll talk about some general considerations first. And then hopefully, if we have time today, we'll talk about the N oscillator or N slit case of diffraction. Okay, so last week we did multiple beam interference from a film. We talked about how film undergoes many reflections, and we went through how to add up all those reflections, both mathematically, and I also gave you this sort of physical picture of like what's happening with all the phasors. So they're rotating through an angle. The angle is the phase difference between each of these beams. And the phase difference delta is related to the optical path difference lambda, big lambda, okay? Does anyone recall how to go from optical path difference, phase difference? We've covered it a few times. I'm hoping by now it's clear to everyone how you go from optical path difference, which you can calculate just by multiplying the refractive index by the geometrical path difference, right? That's optical path difference. But how do I go from that to this angle delta, which is the phase difference between the two beams? How does one go from optical path length to phase? What connects those two? Too early to ask a question. We're all just settling in. Any thoughts? One is a path length. The other is a phase. Even if you don't know the answer, how do we think as physicists? How do we try to like convert from something that we know is a length to something like a phase, which is, does phase have units? What are the units of phase? Well, it has units, radians. But does it have dimensions? No, right? We all know that, right? So I have a path length multiplied by refractive index, which is just optical path length, and I need to go to a phase, which is dimensionless. What do you think I should do? Yes. Some factor of the wavelength, exactly. In fact, we divide by the wavelength, exactly. And then we also multiply by one more thing, just to make it in units of radians. 2 pi. 2 pi, exactly. Very good. So there you have it. Okay, we have reasoned it out, and hopefully you'll never forget it, right? Instead of me telling you the answer, now you all understood why we have to do that. Well, you understood from a dimension perspective, but you also know it from the wave perspective. Wave propagation is k times z, right? K, cosine kz minus omega t. Oh, nice. Yeah, I forgot that there was this poster session. Kz minus omega t, and k is 2 pi over lambda naught. So when we run the wave in distance or path length forward by z, we have to multiply by 2 pi over lambda naught to give you, or 2 pi over lambda to give you the optical phase, okay, the phase of the wave. Okay, and all right, just to conclude, we then showed this equation for the electric field, and yeah, that's just a mathematical addition. And so I talked to you about an application of this multiple beam interference in the Fabry-Perot interferometer or Etalon. Basically, a way to construct this film, you know, and to look at multiple interference, multiple beams, is to take two nice mirrors, which will reflect the beam back and forth a lot, right? And to put them at exactly a distance d apart from each other, okay? So that's two plane parallel mirrors, fixed at distance d. It's commonly used in high resolution spectroscopy and in laser cavities, like I was telling you, like many laser cavities are built from these Fabry-Perot etalons or Fabry-Perot interferometers. And remember, I also mentioned that An echelon is the mirrors are just attached to a block of invar or quartz, which is very thermally stable. And it's an interferometer if you move one of the arms, which most of the time people do want to have some control over that distance. So they may put something to make that move. Okay. And the reason why this is, say, better than a Michelson interferometer, we talked about that as well. These are just the fringes, just very similar to the Michelson. The reason that this is better is because the fringe, the shape of the intensity pattern that comes out of these interferometers is extremely sharp, right? So, and we discussed in the last class an application, if you recall, of how if I have two wavelengths that are very closely spaced, remember we did that problem where if two wavelengths are very closely spaced apart in frequency, you can convert that to wavelength difference if you like, but we did it in frequency, then we can tell them apart with a Fabry-Perot echelon because of the how sharp those narrow and how narrow those fringes are. Okay, that's just the formula. That's the ARI function as I discussed. Okay, and this is the example that I did. Where we zoomed in on these patterns and we looked at what would happen if I sent in two different wavelengths with slightly different frequencies. They would create one for one frequency, and then the other one would be slightly displaced. And we said that they will be resolvable if they're separated by like half the width of this resonance. And the width of the resonance is related to this number for the Fabry-Perot cavity, which is called the finesse. Very important number. And as I was explaining to you, it's just a ruler, right? So this is a ruler. It's got like sharp peaks at all of these different deltas or frequencies. And we convert them to frequency or wavelength, if you like. And then we can separate them if the width of the or the spacing between the fringes is like half the width of this fringe. Okay, and the width of that fringe gamma is just related to the free spectral range divided by the finesse, or the other way around, which is the finesse is just free spectral range divided by gamma. So gamma, finesse, etc. These allow you to tell how finely you can distinguish between two wavelengths. Okay, we did that example in class. I'm just reminding you of it. So finally, to conclude the interference chapter, I just wanted to go over some of the applications of interferometers. We've seen quite a few already, but I just wanted to sort of summarize many of them here on this slide. Oh, and a couple that I didn't talk about. One is optical testing, which is you can use this to in so-called Twyman-Green interferometer, which is basically a a Michelson interferometer. But now we use it to tell how good a test lens is relative to some surface, a curved surface. Okay, so here's a curved surface. It could be a mirror, it can be a surface, curved surface, whatever. And then we compare that to a test lens. I mean, this is how, for example, you could compare in the Hubble Space Telescope, the mirrors that were created, how good were those mirrors could be compared to some reference mirror by using a Twyman-Green interferometer, because you can tell if there's any deviation from the wavefront that you should get from the reference surface, that will show up as interference fringes in your field of view. And you can then parameterize how good your desired wavefront is. We have covered this a couple of times, refractive index determination in the class, and now some of you have also seen it in your special projects. Spectroscopy with the Fabry-Perot, I went over that in the last class. And we also talked about multi-layer, we talked about dielectric coatings, only one layer. We talked about that anti-deflection coating, but you can do multi-layers as well. And now you can understand using multiple beam interference, you could figure out those formulas as well. Okay. Synthetic aperture radar. This is a very interesting application where, for example, you can map the surface of the Earth. That was done by one of the space shuttles where they took synthetic aperture radar. You can think of it as a Young's double slit experiment run backwards. So basically, they sent out radio waves. The radio waves scattered off the Earth. But now, how do you will get some intensity, but you won't be able to tell how high that elevation is. Well, you can tell that by looking at two different receivers, which are spaced apart. And that allows you to tell what the phase of the wave coming back from that reflection is from the Earth. And this was used by one of the space shuttles to build a topographic map of the Earth over very large distances, okay? Very large scale, by just flying over that area. LiDAR is the same idea. So where they use lasers now instead of radio waves, they fly an aeroplane or something like that, and they're like scattering the light off of the surface and then looking at the interference. Obviously, this is a more kind of challenging interference experiment than just radio waves because the wavelengths are smaller, but they're also very great high resolution and give you great information. LiDAR is also nowadays used in autonomous driving vehicles and things like that to build up pictures of what's going on around the vehicle. So, one big sort of career for optical physicists and optical engineers nowadays is in going and designing things for autonomous vehicles. So you should, if you're interested in things like that, you can certainly explore that topic now on your own. I talked about LIGO, that's just a big Michelson interferometer, quantum entanglement. We generate a lot of that and measure it using interferometers. Talked about fiber optic telecom modulators. You may remember with Mach Zehnder interferometers, I mentioned that you can set up you can make a modulator by creating a Mach Zehnder interferometer with fibers and then putting something in the middle to like change the phase. And that allows you to switch using the fringe pattern between on and off, for example. And fiber optic sensors. So this is also another big application. Actually, it's one of the biggest applications for like these kinds of interferometers. You make a Mach Zehnder interferometer, which is very large, and then you monitor the changes in that interference pattern due to changes in the temperature, because that causes the length of the fiber to change, or it causes something else, some parameter to change. So fiber optic, because they can be done remotely, right? So for example, like in oil and gas pipelines, they have these fiber optic sensors, fiber optic interferometers essentially set up so that they can like send the light pulse and measure the light pulse. And then by telling what's happening at different regions along the fiber optic cable, they can measure something about the temperature, for example, in the pipeline, as an example. And laser ring gyros, I mentioned this briefly, that's a ring cavity application. Holography, this is another application. I might have something more to say about it towards the end of the semester if I have time. If not, some of you are doing the special projects as well. Okay, so that just summarizes everything we have learned in chapter 9 or in week 11. Oh, actually, I left off a couple of things there. I'll add it in the actual slide that I posted. Okay, so any questions about interference so far? I'm just reviewing things that we learned, but in case you had any questions, I just wanted to quickly stop that. Okay, if not, we are moving to a new topic, which is called diffraction. Okay, and diffraction is just the term for deviation of light from straight line propagation, coined back in the 1600s by Grimaldi. And it's a characteristic of what happens when a wave is partially obstructed or transmitted. So it can be either, it can be transmitted, but then like the phase, for example, could be altered of that wave. Okay, so this is an example here. So for I don't know if you can see it on the kind of visible to me. I'm not sure somebody sitting in the back could see it. So this is a laser beam which has been expanded and then is used to like this hand with the coin is blocking the laser beam. And if you look very closely, right here and here, you can see some fringes. Okay. Well, those show up much more clearly here, for example, as well, right? This is electrons diffracting from crystals of zinc oxide. And again, like some of this is just due to the fact that they may not be getting directly absorbed, but their phase is changing as they go through this crystal, especially near these obstructions, for example. Okay. So those electrons are, essentially getting changed. So whenever the wavefront is changed, obstructed in some way, either in amplitude or phase. So this, for example, the same thing like this little, obviously the coin is obviously blocking the light, but imagine that was a clear plastic bead. Well, it turns out there will be fringes in the vicinity of that clear plastic bead as well, because the phase of the wave is changing as we go through the clear plastic bead because of the refractive index, as we discussed before. So, okay, so these are all different ways in which diffraction shows up in experiments. But it turns out long before diffraction showed up in experiments or we knew what diffraction was, people observed very interesting atmospheric optical phenomena. Okay, and it is kind of to many people. This is I show you some examples here. This is a cloud. with like obviously in the vicinity of that cloud or in the cloud, there are water droplets. Obviously, water droplets are usually pretty transparent. But you can see that there are these color pattern that is showing up in the fringe or fringes, bands of colored light around this cloud. Okay. Similarly, in like it also shows up, you might see like bands of colors in the sky of like in these clouds. That's iridescence. It was called iridescence. I think corona and iridescence, pretty similar phenomena. And then probably the most kind of famous ones. One of these, I don't know how well. Again, this picture probably looks much clearer on my laptop than it does on the screen. This is the famous Brocken specter. Okay, so this is this scary looking kind of when people were hiking up in the mountains and they were looking down on a cloud layer below them, they saw this like scary looking specter, but then around that specter was like this glory. That's what they called it, optical glory or a halo, right? So they wondered at that time, was this either an angel or a demon? Some people thought it was an angel because you could see this halo, and then if you didn't see the halo, you're like, oh my God, that must be a demon, right? So that is kind of how people were, like observed some of these phenomena and they didn't really understand it. And same with this one. Of course, now with, in planes, you can see as you go above the layer, and the conditions are just right, you will see these, glory again around the shadow of your airplane. Kind of like, I want to put yourself in the shoes of someone who maybe knew about Newton, right? And Newton's experiments with light and the refraction of light and how colors are spreading out when you have some, when they go through some prisms and things like that. And then maybe recently you had read this paper by this guy, this young whippersnapper, Thomas Young, who claimed to know more than Newton, right? He said that light is a wave. And you're like looking around, I wonder if this light is a wave thing sounds new and interesting. Maybe I should explore this some more. Yeah. And you looked at something like this. Could you start to I ask you, could you start to speculate whether this is a wave or a purely geometrical, refractive index phenomenon? What would you think? How would you start to try and answer that? Is there anything characteristic about these patterns, these colors, or anything? I'm giving a hint here that might make you think it's one or the other. I actually mentioned this when we talked about Young's double slit as well. And remember that Veritasium video that I showed you guys. Something about that, and maybe these that might strike a memory card. Anyone talk amongst yourself? Maybe you can. Feel free. What? Right, we know the rainbow, right? Exactly. I heard someone say the rainbow. Rainbows, clearly there are spreading of colors, right? Red to blue, and we're seeing also red to blue here, right? So is there anything about this pattern that would make you think this is just like the rainbow? Or would you say, no, wait a minute, it's not like the rainbow. This is something else. Which colors get deviated more in the rainbow? Or you all know the rainbow. So which color gets deviated the most? Was the rainbow? Anyone? All on a group here. Someone on the spot. Unless someone volunteers. Come on. You know the rainbow. We even did a problem in the midterm on rainbows. Is that why you won't remember? Because you got it wrong in the midterm? Yes, Stephanie, thank you for bailing me. It's okay to be wrong, okay? It's fine.
I would guess it's probably.
Well, that's a good point. Is that what you see here?
I don't know, the colors like repeat, so it's hard.
It is hard, yeah, okay, I get what you're saying. Okay, let's concentrate on this central thing here and maybe, or maybe like, look at this pattern over here. It goes from blue to green, yellow and orangish to red. Yes? Everyone see that? How about the rainbow? So red is clearly going out more, right? It's getting deviated. What about the rainbow? This. Exactly, right? Purple's on the outside, red is on the inside, right? For the rainbow. So this is opposite of the rainbow of the traditional colors that you're used to seeing. Same over there, in the corona and the glories. So, and this, as I mentioned, is very similar to what we saw in that video and also in the pictures that I showed you with Thomas Young's experiment, right? Because red has a longer wavelength, right? So, and wave phenomena, the angles for the Young's double slit are controlled by the wavelength. So the longer wavelengths were getting deviated more. Whereas in the rainbow or in other experiments with like this, it's the refractive index and the variation of the refractive index, which goes as 1 over the wavelength, generally, that controls the deviation. Okay. All right. So this is what a scientist would hopefully, at the time, have realized. Wait a minute, I can't explain this with the usual geometrical optics and diffraction arguments. This is a new phenomenon. Okay, this is more like Young's experiment than it is like Newton's experiment. So they started to move towards Young after seeing all these things, and of course many other things. Okay, so yes, indeed. So the explanation for all this is diffraction or interference. Really, I mean, interference. This is wavelength dependent, and in particular, we are going to understand it using a principle which is called the Huygens-Fresnel principle. And I'll just give the statement of the principle. And this is the sort of the visual representation or picture of what's happening. In a way, we've sort of talked about this before when we discussed things like scattering and refractive index and how refractive index comes about from scattering. But this was now made even for waves hitting any object. So okay, what is the statement? Okay, every point in a wavefront. So here, for example, these little dots here represent points on a planar wavefront. Okay, and these dots are emitting secondary wavefronts. Okay, and this would be true even in a vacuum, according to Huygens-Fresnel principle. Okay, it doesn't need that there are, scatterers here. In the Huygens-Fresnel principle, in the way it was given, is like each of these serves as a source of secondary wavelets, and these are spherical secondary wavelets at the same frequency as the primary wave, and the optical field at any point beyond this primary wavefront, which is to the left over here, or is the sum of all of superposition, including amplitude and phase, of all of these secondary waves. And so to the left here, we kind of see how this picture still results in planar wavefronts. So we have a plane wavefront, it's emitting spherical waves from each of these little secondary scatterers or the secondary wavefronts, secondary sources. And the sum of these, as you can see, is still a plane wave. Okay. And this is, of course, a pictorial representation. I'm not proving any of this. And then this wavefront advances, I get a second set of scatterers. This now produces secondary wavelets. That produces planar wavefronts, and this process repeats itself. But now we come to an obstruction. Okay. And here, the assumption is that all of the wavefronts are then absorbed, but still we have these secondary scatterers that are giving rise to spherical waves. And then as you can see now, the spherical waves can spread beyond the direct geometrical shadow of this obstruction, right? The geometrical shadow, you would only get light in this region right here, right? This region right in front of the slit is where you would see light, and everywhere elsewhere you should not see light according to geometrical optics, if light just traveled in straight lines. But due to these secondary wavelets, there are waves now extending out into the region where normally we would get just darkness, Okay, so to talk about what are the conditions a little bit more carefully in which we observe diffraction, as we have just said that this is the phenomenon of diffraction, we want to understand the path length difference between one point of the slit and the hole in the aperture, or aperture as I'll call it, aperture, hole, slit, etc., in the screen, and the other end of the slit. Okay, so let's look at some point P, which is somewhere out here, this is the point P, and we look at the path length to remember it's just the sum of the wave from this edge and this edge. I'm just taking those two edges as the extreme points in the slit. Of course, we can ask about what's happening at any other point in between, but I'm just taking the extreme points to illustrate what the conditions are for interference. So if we look at AP, the distance to this point P from the one edge of the slit, and BP, which is the distance from the other edge to the point in the slit, the path length difference is AP minus BP, right? Whether it's positive or negative, I don't care at this point, okay? And you can see if P was just directly in the slit, if it was just a point right here in the slit itself, then AP minus BP must clearly be less than the size of the slit AB, the size of the slit. Or you can argue using the triangle inequality in this big triangle that is created by A, P, and B, that will also give you the same result. Okay, so if lambda max, which is the optical path length difference, is just AP minus BP, then by this argument, lambda max, the maximum path length difference, has to be always less than the size of the slit. Okay, that's all I'm saying. Okay, the path length difference cannot exceed the size of the slit itself. Okay, and so now we ask, what do we compare this to? Well, we have only one quantity that matters for a wave, which is the wavelength, right? So if the wavelength can be either greater than this AB, okay, and which is also then greater than the maximum path length difference, or it can be lesser than, right? So, or comparable to, lesser than or comparable to, I'll sort of, classify in the same condition. So if lambda is greater than AB, then lambda must be greater than the maximum path length difference that I can ever have for any point P, wherever that point P is, in the outskirts of the slit or in the center of the slit, etc. So what does all that for? Well, that just says if lambda is much greater than this lambda max, then I'm only going to see constructive interference, because I can never achieve a condition where, say, lambda max is lambda over 2. Because lambda is just so much greater than this lambda max, so I'm never going to see destructive interference. I'm only going to see constructive interference. So I will get waves at regions beyond the shadow. So I can get constructive interference even though I'm in the shadow of the obstruction. Another way, of course, to argue is go to the extreme limit. If this became a point source, right, where AB is almost 0, lambda is clearly going to be greater than AB. We know from a point source, we clearly will get spherical wavelets, and we will definitely get waves or intensity of the wave out in the shadow region. Okay, so that's another way to argue about all that. All that I said basically can be argued by that approximation as well. Okay, and if lambda is lesser than AB, then essentially there's no spreading of the wave. We as soon as we move away from the geometric shadow, we get destructive interference very quickly. All the waves are starting to interfere destructively, and you get destructive interference. You don't get spreading in those regions. Whereas if lambda is greater than AB, you get spreading. This is just with water waves, as to show you that this is exactly what happens. And then what happens in the situation where lambda goes to 0, is much, much, much smaller than AB, we recover geometrical optics. As we've always said, right from the beginning of the class, that's the qualitative regime where lambda is going to 0 is just geometrical optics. Okay, so that was just qualitative arguments, but it's very helpful to keep it in mind to know when you'll get diffraction and when you won't get diffraction. Okay. So lambda has to be sort of greater than the size of the slit, or the size of the slit has to be comparable or lesser than lambda to get this kind of diffraction. Okay. Okay. Everything I've said about this Huygens-Fresnel principle, it was actually made more rigorous. So it's not just a, something that was pictorially represented. It was made more rigorous by Kirchhoff in the 1800s through analysis of the Helmholtz wave equation, which is just Maxwell's wave equation, but just rewritten carefully for like these conditions. And it's again, this still is an approximation. It's usually only valid for apertures that are somewhat in comparison to the wavelength. Okay. And the full solution, which is requiring partial differential equations with boundary conditions, this is a very difficult, analytical problem. Of course, with numerics, we can make much more progress on it these days with like numerical techniques. But back then, Sommerfeld, in a very huge advance for the field, at the time, he gave one of the few exact solutions. And, if you want to learn more about these things, you should go to grad school and take some of these and read some of these textbooks as well, which are very famous in the field. Okay. Before I go on, though, it's kind of, something that puzzled me as a student when I was learning about this was, what are these secondary scatterers and how can we ever justify them? The secondary wavelet sources and all that. It seems nonsense because, we have atoms, either when it's in the air or so on, that are absorbing or reacting to the electric field of the light that's incoming. And similarly, when I put a slit or something in there, the only place I know that there are no atoms is in that slit. I mean, there may be a few air molecules there, but generally speaking, there's no scatterers there. There's nothing that should be re-radiating light from that empty region where the hole is. So why does this work so well? How can it be that something that seems physically not intuitive? Because instead, I would say the intuitive thing to do, or the right thing to do, is to take all the atoms in the screen, calculate the waves that are radiated by those atoms, and add them up. That's the right physics approach to what's going on. Instead, these Huygens and Fresnel people, they seem to argue that, I can ignore that entire screen and just talk about only what's in this empty. So to me, at least at the time, I was like, man, this makes no sense. Okay. So it took me a while to understand this. So I wanted to convey it to you also, which is that when an electromagnetic wave is incident on a metal or opaque screen, the electrons are in a thin layer of atoms are absorbing and re-emitting the light. Okay, so this is just the same picture we had when we talked about the refractive index. We said that there's a layer of atoms right at the interface. They're basically responding to the electric field, and the electrons are shaking up and down and scattering the light. Okay, so that's exactly what's going on in a metal or any opaque obstruction, except in an opaque obstruction, it just cancels the field completely. Whereas in a dielectric transparent medium, it only cancels the field partially, but it slows down the field in such a way that we get the refractive index or the change in the velocity of the wave in a transparent dielectric medium. But in an opaque medium, basically that cancellation is perfect. So there's no more electric field beyond the first few layers. So even if the first layer of atoms in the metal doesn't cancel everything in the forward direction, the next layer will cancel some more, the next layer will cancel some more. In fact, there is a well-known formula for the thickness of a metal that you need to cancel all of the field going into the metal. This is called the skin depth. Okay, and this is the formula for the skin depth, which is here. I'm not proving it, but I'm just giving it to you. This rho here is just the resistivity of the metal, or conductive 1 over the conductivity, if you like. So the higher the conductivity, as you can see, the delta, the thickness will be smaller and smaller. Just to give you an idea of like real numbers here, let's take something like not optical, even just like a microwave frequency of 10 gigahertz. Then if you take various metals, aluminum up to silver, silver has one of the highest conductivities in the optical domain. And we find that, it goes down to like hundreds of nanometers, basically, for microwave frequencies. Now, for optical frequencies, as you know, the frequencies are on the order of 10 to the 14 hertz. Okay, this was 10 to the 10 hertz, 10 gigahertz. Optical frequencies are 10 to the 14 hertz. So in this denominator, I have a factor of 10 to the 4, let's take the square root, that's factor of 100 smaller. Okay, so the skin depth for light is on the order of nanometers. Okay, 10 nanometers approximately for various metals. Okay, so it's a very small thickness. That's all you need to completely absorb the light or reflect it back is what happens in a metal. Okay, so knowing that, we just will now discuss what happens when I hit an opaque screen, a metal screen like this. I have an incident field, and then I have this metal screen or opaque obstruction, and I'm focusing in on this one region here, which is where I'm going to remove the opaque obstruction later to make a hole. Okay, and I'm going to argue that the total field, we already said the total field beyond this obstruction is 0 because the obstruction is there, right? So, and we just said that a few layers of metal are enough to completely destroy the field or make it go to 0. Okay, and now I can say I'm going to make an approximation, which is well known in solid state physics. It's the independent electrons approximation, which means that all the electrons here are independent of the electrons over here. So if I remove these electrons, I don't affect the motion of those electrons. Okay, so I don't change the problem by just removing those electrons or those atoms that are in that hole over here. So let's see. So electric field is 0, but we know it must be the sum by superposition of everything that's incident plus whatever is scattered by this metal field, metal screen. And in particular, we're going to focus in on this little slab over here because that's the part I'm going to get rid of. Okay, so if I remove just that contribution, then my electric field over here must be 0 minus that contribution, right? So that must be 0 minus the scattered field from that disk. Okay, so this argument tells you that the field in this region is indeed just the scattered field from the hole and not from all the electrons over here. Okay, that's what this is saying. Okay, this is a very subtle kind of argument, but it proves, I say, air quotes, the Huygens-Fresnel principle, except for the minus sign, which actually turns out to be interesting. We might come back to that when we talk about Fresnel diffraction. But okay, so I have a few more minutes. Any questions on this argument? This is not in your textbook, but I found it confusing when I learned this topic, so I wanted to explain it. Maybe none of you found it confusing, but I wanted to just talk about it. Okay, so now I want to talk about Fresnel and Fraunhofer diffraction. Okay, these are the regimes of diffraction, or the sort of various types of diffraction that you will observe. So the problem or the way in which we classify this is by considering where we observe the diffraction pattern. Okay, so we can start by observing the diffraction pattern very close to the slit, or the obstruction and the hole in the obstruction, or we can move it away and observe in another plane over here. And so as a function of this distance r, we're going to see that there are various characteristic regimes of diffraction. Okay. So just over here, I drew sort of what I might expect in the geometrical shadow, right? In the geometrical shadow, I would just see the image of the slit, right? I would just see a place where there was no light, and then right where the slit is, I would see some light, and then I would go back to 0 outward of that region. Okay. And now, when I actually observe the different patterns of light that I see, and this is R is increasing over here, R increases in this direction upward. Okay. What I actually see are these fringes. First, I see a fringe pattern that looks like this. Okay. Well, that was sort of to be expected from our argument, but you notice the fringe changes, this pattern changes as I go from here to here to here to maybe here. It's the number of fringes, the way in which they appear, all of that is changing as I go in this region. Okay. Now, once I get past this region to this region over here, you can see the pattern doesn't change, but it just spreads out. Okay. So this is called the far field region or the Fraunhofer region. And this region, where things look just like the geometrical shadow, it almost looks like the geometrical shadow, except that there's some fringing going on. Okay. Well, maybe around here it starts to resemble more of this, but it isn't quite. This is an intermediate, so it's not quite as clear. Okay, but so I would say, yeah, so we break up this thing, it looks something like this and like that. One is Fraunhofer, one is Fresnel. I'll make this a little bit more concrete or rigorous in the next couple slides. But this is just to tell you what you would actually observe and how we classify the difference between these fringes. This looks almost like a geometrical shadow, and this will be a common theme you'll see when we do Fresnel diffraction, that the pattern that you see will look almost like the obstruction or the aperture plus some fringes. Okay? And the fringes can be even inside the geometrical shadow. Look here. There are fringes going on even inside the region where you would expect, not just inside the shadow, but in the light region. So this is where I would get just light. Normally, I would just expect a bright region here. But now I see there are fringes even in that bright region. And I see there are fringes outside the bright region. Okay. Whereas this one is much more uniform. I get some, I get a central bright region, which is maybe spread out. And then I start to see fringes in the shadow region. Okay. So we can make this more rigorous, as I just said, by talking about the Fresnel and Fraunhofer conditions. And the first thing I would want to say is that for Fraunhofer diffraction, the situation is such that the incoming and the outgoing waves are nearly planar. Okay, so we've talked so far about the incoming waves. The incoming waves are always usually assumed planar in our situation in the Fraunhofer diffraction. But the outgoing waves, if they are also nearly planar, so meaning we are in the far field, very far away, of course, everything looks sort of like plane waves, then we'll get the Fraunhofer diffraction regime. Okay. And as I'll show you, if I take y, which is a aperture variable, which just tells you what is the position of a point, a secondary scatterer from the Huygens principle inside the slit, y is a variable that tells you where that scatterer is, then the path difference between different parts of this interference pattern will be a linear functional aperture wave. I'm just saying that. I will show you in the next few things. And the Fresnel region will be where I move either S, the source, because of course if the source is very far away, then its waves are planar, but I can make it also not planar by bringing the source close to the aperture. And now I can similarly make the observation point, instead of being far away, bring it close, then that also makes it not planar anymore. And the last thing is, of course, I can make the wavelength smaller. And why is that? Because, of course, when the wavelength gets smaller and smaller, small changes, the curvature of the wavefront starts to matter. Okay? That is the other way in which I can actually make the wave curvature or the wavelength matter to this problem. Again, I'll prove this in this next slide. This the Fraunhofer condition is this, that R, that distance where I'm observing things, must be greater than b squared, b being the dimension of the slit or aperture, squared divided by lambda, the wavelength. Okay. And why is that? Why is that condition there? This is not in your textbook, but I just wanted to explain it to you. Okay. So, as I've just said, if I can make either the incoming or outgoing wave more spherical or more non-planar, then I'll get the Fresnel regime of diffraction. Okay, and if I make it more planar, I make it more Fraunhofer condition. Okay, and planar relative to what? Again, relative to the wavelength. Okay, so if the phase difference between a point over here, this is a point over here. Okay, and if the phase difference for waves that come from the edge of the slit to the center of the slit, that's this phase difference, right? So if this is a spherical wave from the center and this is a spherical wave from the edge, they travel slightly different path lengths. One travels the distance r, capital R, which of course this is the spherical wavefront that's coming from that central region, and this one travels only a distance smaller. Okay. Now, if this is true, now if r and small r are different, right? And that difference is clearly this delta over here, this little small amount. If that is on the order of a wavelength or comparable to wavelength, then you start to get the Fresnel region, because then this curvature of this wavefront matters. You can see that the wavefront is actually curved. If you can't tell what delta is, if delta is much smaller than a wavelength, then this thing looks nearly planar and you get the Fraunhofer condition. So then from then onwards, the physics, understanding that physics, the math is just very straightforward. We know R equals, this R is the R minus the delta, which is that the path length difference. And I just need to calculate it. Well, from this, this triangle over here, use Pythagoras theorem to say R minus delta the whole squared plus B over 2 whole squared must be equal to R squared from that triangle. Okay. And now you can just expand, we just square that and then neglect terms that are higher order in delta. You get that delta is on the order of B squared over 4R. Okay, and as I've just said, the Fraunhofer condition is if this phase difference or path length difference is much lesser than lambda, I get Fraunhofer. The wavefronts emitted are nearly planar. Okay, and that means I put that in, I get R must be greater than B squared over 4 lambda. Ignore the 4, right? B squared over lambda is good enough. Okay. So this is the derivation or proof of the Fraunhofer condition. Of course, I did this for assuming the incoming wavefront was planar and the outgoing wavefront was spherical, was no longer planar. You can also do it for the incoming, and so the same condition can also be put on where the source has to be. So if I have another distance, call it S, capital S, where capital S is the distance to the source, right? Then similarly, S must also be greater than B squared over 4 lambda to make the incoming wavefronts look planar at the slit. So we have a condition both on the distance of the source to your aperture and the distance of the screen to the aperture. And last, I want to just point out that in the lab, it's much more practical not to have to put your source and your image and your observation point very, very far away to satisfy this condition, but instead to use lenses. Okay, and the reason is at least for the let's just concentrate for the incoming wave. If it's even if the source is close by, can be made nearly planar by putting it at the focal length of a lens. Right? We know this from geometrical optics that now the image will be at infinity, which is effectively like planar wavefronts coming out from the source. But similarly, we can do the same for the image or the screen. Okay, and the way we do that is we put this lens lesser than a focal length away so that it doesn't form an image of this actual aperture. So the actual aperture is not being imaged onto the screen, but instead what's being imaged are the planar wavefronts, because only plane wavefronts coming from this screen will get focused at the aperture. So effectively, it again satisfies the Fraunhofer condition, both on the source and the image or on the observation point. So this is how we would observe a Fraunhofer condition in the lab for both the source and the actual observation point. Okay, last, so that's just a summary. I'll just put that there. And the last thing, because I know you all came for just the quiz. So here's the quiz for today that you should fill out in your Canvas, but I will talk about it in the last 1 minute of the class. So a microwave oven with microwaves with frequency in the gigahertz region has an opening of about 30 centimeters in the front. Let's say the microwave safety interlock fails, right? That's not good. Okay, the microwave, you know what I mean, like that it'll stop as soon as you pull the door open, right? You can defeat that. Okay, so the microwave generator could remain on while the oven door is open, and this thing is putting out hundreds of watts of power. Okay, so that's not safe. So it is found that food placed right in front of the microwave at a distance of 2 meters, 6 feet approximately, gets cooked with long enough exposure. While food moved out of this direct path by about 30 centimeters does not get cooked. Okay. What can you conclude about the wavelength of the microwaves used in the oven?